All right, so cosmology, not cosmetology, and it's not just the same people that confuse it that say when we talk about astronomy they say astrology, although they're about on the same par, astrology and well, cosmetology. That's a real job, I should say. I shouldn't say that. But at any rate, neither of them are space science. Cosmos, okay, the universe, everything that's out there. What have you been? Whoops! How did I jump 6 pictures? Good luck. What have you been staring at there as you were reading those words, intro to cosmology? What is this a picture of? Stars. I heard stars. Huh? A Milky Way. Galaxies. Milky Way being a galaxy. What are you staring at when you look up at night? Outside when it's clear. Probably not in Utica. What are you seeing out there then? Stars. Some people said some galaxies. Are you seeing galaxies? Well, not like this, huh? But, yeah, if you know how to tell a star from a planet, you could tell the difference between that. Very good. And you guys should at this point, right? We've had enough of this, stars twinkle, 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 little stars, actually, science lesson, right? They oscillate. The light comes from so far away, it goes through so many atmospheric shifts that it fluctuates just enough to make it look like the light is wavering and flickering. Stars, huh? No, those are asteroids and meteorites, and they don't really. That's one of the places I'd love to expand this conversation, but certainly not in cosmology. No, that would have been back in the previous stuff when we were talking about in the solar systems and whatnot. But so shooting stars are not stars, for record there. So sort of back to the point though. And planets don't twinkle. Planets are solid lights. They're reflected. They're a lot closer. Even I know we just made the hallway solar system, and you guys know how far away some of those planets are. They're still way closer than the closest star, and you're not seeing those far, far, far away ones anyhow with the naked eye, because it's just reflected light and it's just not bright enough. But so back to the premise. This picture is full of galaxies. Okay, yeah, arguably there may be a star in there somewhere. And when you look out at night, for the most part, you are seeing stars, but you are also seeing plenty of galaxies. All right? You just, you don't have the magnification in your eyes, so on and so forth, to see them in their spiral nature, their dumbbell form, their whatever different shape that the galaxy's hourglass is another one, may happen to have. They just look like pinpoints of light. But if you could twist your ear and magnify your vision, okay, then these might come into focus. You'd be surprised how many things you've been staring at, thinking they're stars and they really aren't. Sometimes even they're nebula, which you're going to see in a little bit, which isn't a star either. So this is a really big area of space that you're looking at. And this is something we're going to do, trying to stretch your brains out a little bit as we go through these next handful of slides. We're going to get big and then small and then big and small. So we're going to zoom in on one of those galaxies, and we're going to go to a really, really dense part of it. All right? And this dense part is just another random vocabulary word. It's called a star field. Pretty descriptive, I suppose. And talking about distance in space, it's so hard to judge, of course, how far stuff is away, both sort of directly away from you and then side to side from you. One of the things that I like to point out when we talk about the constellations is that, we're used to that sort of planetarium ceiling. Okay, you guys have a vocabulary word for that, and you'll see it on the test. We talk about that planetarium ceiling and the assumption that, let's say, Orion, right, all of those dots that make up his shoulders and legs and his belt and his sword, they're all just right there, dotted on the ceiling. But in fact, one of them could be 3 light years behind or in front of one of the other ones. There's not necessarily any connection whatsoever, except for that implied ceiling. Same is true here. And I've tried over the years with this picture to give you guys some idea of scope. How far away is our closest star? Anybody remember? What is our closest star called? The sun. Oh, good. We know that one. Not everybody remembers that. Not everyone remembers that the sun is a star. So the sun is 93 million miles away. Pretty close, all things considered. The next set of stars is 4 light years. All right, you're going to see very soon how far a light year is. Suffice it to say, it is a lot of times more than the sun is away from us. So even if we put somewhere in between that number, in between each and every one of these stars, holy smokes, that's a lot of landscape, right? I hazard to say that because it's so dense, that the stars are actually a good bit closer than that. I don't have the physics behind me to say, that an average star can only be this far away from the other one before they, attract to one another and collide in a fiery mess. And that does happen. But, so there's got to be a certain amount of distance between these guys. Anybody counted while I'm talking because you're bored and just staring at this picture? How many stars are on there? Yeah, a lot, right? I like 73 maybe. Maybe a little more. Carl Sagan used to get teased, primarily because of the way he said it, but he used to say there were billions and billions and billions of stars in the galaxy, and that's just our galaxy. Okay, this is another one. I don't know. I should have labeled which galaxy it's from, but there's a lot of stars in there. Okay. So I don't know. We zoomed in, so we kind of got small for a minute, but I used that zoom in to try to give you an idea, if I could go back a slide for a moment, of how big, just one part of one of these is. So big, little, big, again. All right. So my trick question won't be a trick question. Usually I rely on someone to say, wait, I thought the sun was our closest star. We already got that out of the way. The next closest star is actually a system of 3 stars. We're pretty sure. And it's the Centauri system. You may have heard of Alpha Centauri. All right. And this is also an interesting side conversation on the technology and science. Basically, the evolution of telescopes. When we first looked at this, it just looked like a closer version of what you could see. You could see this one with your eye. Okay, you could see something many trillions of miles away with your eye. But it looks just like a pinpoint of light. And it continued to do so for a long time. Then all of a sudden, telescopes got a little better one year. Somebody bought the next model and said, holy crap, that's actually 2 stars. So they had Alpha Centauri A and Alpha Centauri B. Alpha and Beta. Alpha Centauri. Then, I think it was a good jump in time. We'll say 100 years. I don't have a number, but a good jump in time. They realized that there was actually another star that was in a gravitational sort of arrangement with them. And there's a third star. And that one was actually a hair closer. So they didn't whip out Alpha Centauri C at this point. They gave it a whole new name, Proxima. All right. So technically speaking, and I don't think I get this technical on the test, Proxima Centauri is our next closest star by 0.1 light years. But if you're going that far, you may as well go all the way to the originals, right? So the Centauri system. In all fairness, that's what it looked like. It's the bright one in the center. So it just looks like a big, bright star. When we zoomed in with our newfangled telescopes, they saw the two dots. And I don't have another slide to show you Proxima. I usually point to... My mouse isn't going to show up. There it is. That guy. Right there. Or the one next to it. It doesn't really matter. Anyone plan on going there? All right, so it doesn't matter. Basically, they watched them, and they saw that how they interacted, and that's more so of how they realize that they're connected to one another. They're a system. Okay. So the big thing everyone always remembers from Star Wars is watching the. Is it the double? Now, see, I'm screwing up my own memory here. Is it the double suns or the double moons? I think it's a double sunrise on Luke's home planet. So this, in theory, could actually give you a triple sunrise, which would be pretty neat. I'll have to ask my daughter. She won't know. Hey, is it two moons or two suns we can see in Tatooine when Luke's standing there looking out? No, not you. Oh, that's right. I didn't actually text my daughter. Okay. She would tell me that she knows the prequels much better. That's her genre. So I mentioned light years. And it was pretty abstract for you. Not that you guys have any idea of what 5.8 trillion miles, we'll round up to 6 trillion miles, is, let alone 1 trillion, right? Can you picture a trillion of anything? I can't even picture a million of something. Yeah, it's way too big, right? And this, of course, is why they made these words to equal things. We're going to see another one. I don't know, I might have gotten rid of it. They also use parsecs and AUs, astronomical units. AU is 93 million miles. It's distance from the sun to the Earth. And then there's another one. I think parsec is like 3 light years, I think. Don't worry, it's not on the test unless it shows up. But so we made these units to help folks who deal with this on an everyday basis, to give them some, consistent idea what they're working with. So to round, we're looking at about 24 trillion miles to the next closest star. So 93 million to the sun, 24 trillion to the Centauri system. So in the hallway, when I told you guys, let alone getting around in our solar system was difficult, hop into other solar systems, hop into other stars, okay? 24 trillion. This is in our system. So we're going to need some fantabulous way of traveling for this to ever, ever, ever happen. When and if you see numbers on the test, they will be rounded, okay? Oh, here's AU. Okay, so you might even see parsec then. I have to say roughly, because you know from aphelion and perihelion, right? A couple vocabulary words from the last lectures, that we're not always 93 million miles away. Sometimes we're closer to the sun than others. Anyhow, they will sometimes refer to things as 1 AU or 1,000 AUs, depending on what you're talking about, Pluto or something. But again, I argue that that's just as abstract. So I don't know who it's really helping. All right, let's get really small now. Zing you right back down to Earth. We had a good bit of conversation about the moon in here. So you knew this already. 250,000 miles. Or 250,000. What sounds farther? 250,000, doesn't it? 250,000 is the same, of course. They do that at the restaurants too. They say, would you like a 1/4 pounder or would you like a 4-ounce patty? I don't want a 4-ounce patty. That's little. Ounces are tiny. So they say 1/4 pounder. Oh, that sounds big. So keep an eye when people are talking to you about numbers. There's a lot of ways to be deceiving. So, even though one of you in this room knows the answer to this question because you put it up in the hallway, I want the rest of you to guess randomly, maybe accurately. So, you got to think about what the point of the space station is, and it's to, help us study in space. And I've indicated a few other potential things that it's useful for. You just found out where the moon is. You found out where the sun is. You maybe have an idea where Mars is or whatever. So where's this space station? Where is it? How far out did we put it so it's actually helpful to us? Give me some numbers. Feet, you got miles. You got kilometers. You could use light years if you want. I don't care. Just be a couple. Huh? 200 miles. So like from here to Rochester? Okay. Anybody else? All right. Well, so I actually groomed you guys fairly well. It's not that horribly far away. Usually we get thousands and thousands of miles for answers. And we may have even talked about this for a little bit. If I had a brownie, you'd win a brownie. Yeah. Yeah. So the next question is what's the point? If it's like from here to Rochester to go to the space station, and you're going 250,000 miles to the moon, it's like getting on a road trip to LA and getting off at Oneida to pee. What's the point? There is a huge point. What is it? You might have a better view. Is that what you? Yeah. Okay. That's definitely true. I don't know. It's not the main reason, but that could be a reason. Definitely have better panoramic windows. I agree. What else? Do you remember? You did space station, right? Yeah. Why is it there? Pressure's on now. Okay. That's what I thought. All right. So, do they have gravity up there? You guys know that. You've seen any space station videos. You watch the astronauts in the space stations all the time. You're like 12-year-old kids still, right? 8-year-old kids? No. Maybe some of you. I just went up there long enough for you to see it. It is. Water goes like everywhere, right? Yeah. So you've seen some of the videos. So if the water goes everywhere, that tells us that there is or is not gravity up there. Not gravity. Good. Well, That is definitely something going on. They're studying bone mass and reduction, radiation exposure. All that's going on. But with regard to the fact that it's supposed to actually be what Hollywood has taught you that a space station is a stopping point to other places, right? It's an airport, okay? Essentially. Right now it's been a research station until technology catches up with it. But the point is it's an airport, a spaceport, which we have, by the way, on land as well. There's like a handful out west, a couple out there already. They're waiting. It's above the atmosphere, okay? It's above the gravity. Remember we talked about those rockets, and you saw Apollo 11 the other day, and you've got, I don't know, we'll say 150 foot of missiles sitting there on that launch pad, and just a little ice cream cone on top, we told you, was all the actual habitable part. Everything else was what? Fuel. So the idea is, and this is what the space shuttle figured out how to do to some extent, was to make a reusable object to get up to the space station and back, and then we launch stuff from there to Mars, to the moon, to wherever. Because it's such a huge, huge, huge drag to get up off of the Earth's surface. So they don't even want to do these terrestrial launches anymore. They want to, start with these aerial launches. So you've got a high-flying plane already that carries up some sort of weird little shuttle-y thing, and that takes off from up there. Again, you're in the upper parts of the atmosphere already. It's friction, it's gravity, it's a handful of things that they want to get away from. All right, that's the point. And that's why 220 miles is just right. All right. So let's get big again. This is a very famous photograph that you guys aren't old enough to be around when it came out. And at least it's in color. It's not black and white like that Apollo stuff, right? The 90s, they did have things in color. So this is from the Hubble telescope. And the Hubble telescope was a big whoop-de-doo. It was basically our first, but the first public knowledge, pop culture sort of scientists are putting up this cool new telescope in space. Everyone was waiting to see what it could see. It was a big thing. It really was. And if you're ever bored one day, Google Hubble images and you'll see some neat stuff out there. So this was one of the more famous ones, The Pillars of Creation. Pretty lofty title. It's actually part of the Eagle Nebula, which is not quite so lofty. And the names of some of these nebula are like constellation names. You got to look at it and say, I don't see it. Cat's Eye actually looks like a cat's eye nebula. But some of these, you'll see the eagle in a minute when we zoom back out. So, anywho, famous picture. And so the scientists, okay, this is a nebula. They know what a nebula is. You guys don't yet. So we'll find that out in a minute. But suffice it to say, those are giant clouds of gas and dust, okay? Way out there in space. Really hot stuff. So they wanted to know what those pinpricks of light were. Because we hadn't seen anything like this before. Like, all right, we know what a nebula is. We know what it ought to be. But what are these glowy spots? So that was something new and neat. Here's the rest of it. And again, I don't see an eagle. But if you do, good job. So this thing is 7,000 light years away. It's 9.5 light years long, tall. There is no up or down out there. So it's kind of hard to judge, but it's 57 trillion miles long. The idea behind a nebula, just to give you a little spoiler, is the definition you'll have is that it is a cloud of gas and dust that either condenses to form a star or is left after a star explodes. And then the assumption is that it'll condense into another star. We'll get there, though. So this is a cloud of gas and dust. And the bright spots, it turns out, are these areas where that condensing is starting to happen. Where if you rub your hands together, it gets warm, right? So this condensation is sticking together, not condensating like on your glass of iced tea in the summer, but condensing. And what happens is these particles stick together, they get bigger, they have more mass, they're that much more likely because of gravity to pull something else to them, and it just, the snowball effect, it increases logarithmically, it goes crazy. So these are those points where it's collapsing and it's getting super, super hot. So then they had to figure out if this was going to condense into one star or a couple stars. I think they decided that a nebula just goes to one star. Just has a couple different starting points. Again, totally new science. And if you think about our sun, 93 million miles away, right? Looking around the room at a handful of skin tones in here, if a couple of you stood in front of it for more than a couple hours, you'd end up pretty crispy. I'm a little luckier in that respect. If you stare at it for even a couple seconds, burn out your retinas, right? So maybe 57 trillion miles worth of gas is appropriate to make something that big and hot and everything else that it is. Seems big, right? A lot of gas. But So if you didn't write it down a minute ago, see the point of paper straws, but they're useless. Stellar nursery is a cutesy way of referring to nebula. They do make stars. And after a star explodes, I was just going to say, who knows what it's called when a star explodes? After a star goes supernova, it leaves behind a cloud of gas and dust, as you can imagine. And over time, once it cools down, so on and so forth, it'll become another star. And that's really important because it talks about something that we can't really get into in here too much. It's not an astronomy class. We only have so much time, but it's called stellar evolution. And first, second, third generation, so on and so forth, stars. And what's so important about that is that's how we get our elements. Stars can fuse. They start with hydrogen and helium. And they can fuse up to iron. And I know you don't know where iron is in the periodic table, but trust me, it's not too horribly far. So the question for these folks was, well, how did we get everything else if we believe in stellar evolution and elemental synthesis, et cetera, which they do? How do we get everything else? Well, the answer was supernovas. So a star lives out its life. It fuses all its hydrogen into helium. And then, as you may or may not know, sometimes it contracts or it expands. You've heard of red dwarfs and brown dwarfs and all those things because they have silly names. Kind of stick in the brain if you've heard it once. And again, we're not getting into any of that stuff, but I just want to just give you an idea. So it fuses a few more things as it's shrinking or growing there until it hits iron. Right? And then the whole thing just collapses in on itself, typically, and explodes. And it takes all those elements and then fuses a whole bunch of stuff past iron. Then it goes into a nebula, and then it builds another star just out of hydrogen and helium, but all that other riffraff is still there. Kind of like how our solar system formed out of the leftover riffraff. And over the generations of cycling through of the stars and the supernovas, you get more and more and more elements. When our sun explodes, probably another 4 to 5 billion years, they think we're like right in the middle of our sun's lifetime. It'll explode. It'll make new elements, and however gajillion years later humans take to evolve again and make a new periodic table, if we still think that's important, there should be some new elements on it. So, at least that's what they tell us. All right, let's leave the galaxy finally. Andromeda. You've all heard of Andromeda. All right? If not necessarily the galaxy, you've heard of the Greek lady. Our closest galaxy is Andromeda, and you'll learn why we study it, not just because it's the closest, but it's also very much like our galaxy. It is 2 million light years away, and 220,000 light years in diameter. So it's big. But kind of far away. We like Andromeda because, like us, she's a spiral galaxy. And we'll never be able to get a picture, well, I shouldn't say never, it's science. We will probably not get a picture like this of the Milky Way, because where would you have to go to take it? Way outside of it, right? So they have good reason to believe we're a spiral galaxy, watching the way other stars move, or and so on and so forth. So they said, okay, well, we can't get outside of our galaxy. Let's see if there's other spiral galaxies out there. We found some, and we watched the heck out of them. And then we apply that knowledge to us. Again, we're not going to talk about the Earth a whole heck of a lot here, but I just wanted to take a moment and give you a little perspective. If this were the Milky Way, where's my mouse? Can you guys see my mouse? I can't see it at all. All right, well, let me look on here then. Yeah, it's not even showing up on my screen. We're out here-ish. All right. I suppose there's less riffraff over here. So we'll go down here. We can see a little better. All right. Doesn't matter top or bottom. They say the western spiral arm of our galaxy, but I don't think they use north, south, east, and west in space, right? So that's probably just a Earth kind of reference. But point is that we're kind of far out. And that's a decent place to be. Again, you don't want to be too close to other stars and all that other riffraff. What's that big bright thing in the center there? Some wild guesses. Is it a really big star? Well, it's a black hole. So we don't want to be you don't want to be too close to the black hole. Why isn't it black then, right? The problem is because of that. There's been a handful of movies semi-recently about this. So you guys have more black hole knowledge than the students maybe 10 years ago. They're a huge gravitational pull, right? So what you're seeing there is what they call the event horizon. It's all of the light struggling to escape from there. It's sucking in even light to it. And I always wondered, why they had to say even light, like light is so special. Well, light is special. For one thing, it's practically massless, which is why they're surprised that light's attracted to it. Right? It's that strong of a gravitational pull that even light can't escape from it. So that giant bright spot is actually a black hole. So you don't want to be too close to that. You don't want to be too close to that. So we're kind of good out here in the boonies, all right? And again, it's a little farther to your next neighbor, but again, so far that's served us well. So see the number up there, M31. It's Messier. I don't know how to pronounce it. Messier. I think they dropped the R. I'm assuming it's French. It's a cataloging way. Okay. It's just a reference number. And you'll see that as, again, if you're bored and you find yourself, after I've inspired you in this lecture, to go out and Google space pictures, you'll see M. And then there's also NGC, which I've just decided is National Galactic Catalog. I have no idea what it stands for, but it sounds like a thing. So, but you'll see those M numbers and the NGCs. There's a top view. Not of Andromeda, but of another galaxy that happens to be oriented that way. Again, we're kind of limited in what we can take pictures of. Kind of like being at the zoo, all right? We can't change our perspective that much. So the arms now, to be out in one of the spiral arms, as I was saying, it gives you a little more idea of what we're actually looking at. As I said, they take lots and lots of pictures of spiral galaxies because they're really trying to learn about the Milky Way. And there's a profile picture as well. So the Milky Way, in case you didn't know, is the name of our galaxy. A lot of interesting facts on there, some of which are testable. But I prefer to tell my little fractured fairy tale of a story about the Milky Way instead. I've mentioned a couple times over the semester what I call the early observationalists, these early scientists, right? I may not have used that word, but I've mentioned many times that these people who get their names in the books, they're not the first people to think about this stuff, to wonder about this stuff. They just happen to be, the right place at the right time and get their name attached to it. We've been doing science or thinking about science since we've been thinking, I like to think. And way back when, take yourself, if you will, to a hillside in Greece, and the shepherds are out watching their flock for the night. Much of our early science comes from shepherds because they had a lot of free time, right? That's what you need to do science. You either need to be, you need to have free time. And how do you do that? You're either really rich and you have plenty of free time, or you're not so rich at all and you're a shepherd and you can just hang out in a field and stare. We had this for glacial geology as well. A lot of our glacier terms come from shepherds. Anyhow, so they're sitting back on a hillside, watching their sheep, eating their sheep cheese, drinking their sheep wine, and they're looking out, and someone looks up and says, "Oh, it looks as if the gods have spilt a glass of milk across the sky." Because the Milky Way, anyone seen the Milky Way? You don't have to do it. It's not real hard. You could do it. You just have to go up where it's kind of dark. And you're going to say, wait a minute, I thought it was clear tonight. What's that long cloud doing there? It's the Milky Way. And use that app that you're going to get for the stars to prove it to yourself. You'll see it. It's neat. It's fairly easy to see if you can get up north. So anyhow, they didn't have anywhere near the light pollution we have, so it was a lot easier for them to see. So they're sitting there drinking their wine, and they're looking up, and they said, "Oh, it looks like the gods have spilled a glass of milk across the sky." Except they don't speak English, right? They speak Greek. And the Greek word for milk is galactose. So, years come forward, and we find out what they're actually looking at, and it's sort of an homage to them. We kept the galactic part of it, and we call it a galaxy. And also we left the lactose part for one of the enzymes that's in there. fourth bullet's kind of impressive. You're not going to make a trip around the galaxy in your lifetime. None of us are. Dinosaurs had come and gone. Good 140 million years worth of dinosaurs came and went before one sweep on a clock, if you would. It's a long time. Now, the other day, they were talking about all these different ways that you're rotating, and the fact that you're rotating many different ways at once. And I get it. I really appreciate that. But this one has always sunk in with me. Again, if you picture the clock doing an hour, okay, and you time one, and then to make it all the way back again. That's one rotation around the galaxy, one trip around the galaxy, 200 million years. And to do that, we're still traveling at 558,000 miles per hour. That's mind-boggling. You don't notice it because your desk, your phone, your cat, everything else is traveling at 558,000 miles per hour that way. Same reason you don't notice that you're also going this way and that way while you're going. I'm not that talented. I can't even play piano because I can't do two things at once, let alone drums that has four things. But I can't get myself rotating enough ways to simulate that. But you don't notice any of it because everything around you is doing the same thing. So if you oohed and awed, by the way, before we switch screens, at Andromeda for being 220,000 light years across, we're half that size, 100,000 light years. So Andromeda is super big compared to us. They've guesstimated, that we got about 200 billion stars here. And this, of course, gets into that whole search for other planets stuff, which is a neat field, an admirable field. They've recently figured out a handful of ways to narrow it down, make it a bit easier to do. You may have heard of the Goldilocks zone, right? They look for other planets in the 93 million mile-ish distance from a average star, which is what we've got. The sun's like a C student, really, as far as brightness and temperature and age and all that goes. But we haven't looked everywhere. We can't look everywhere. So, who knows what they'll find one of these days. We can get this perspective in the Milky Way. Looks kind of like a star field, right? I'm not sure which direction this is looking. I apologize. But this is one of our good telescopes aimed at that same cloud of dust you'd be looking at night. One particular part of it. And I do encourage you this summer to whip out that app. If you're somewhere relatively dark, it's clear out. Try and find the Milky Way. Once you find it, you'll never lose it again. And it's kind of awe-inspiring to see. So the Milky Way, the sun, as I told you, is kind of on the outer rim there. The unfortunately named central bulge. All right, that's our black hole we talked about. And nucleus, nobody ever uses nucleus. I don't know why that's even there. And then those are just called spiral arms. Not labeled, but not difficult either. Is this a picture of the Milky Way? No, good answer.
Why does it say photograph?
Well, because it's a photograph of a spiral galaxy. But they're just, no. Good question. Yeah. We think. We're pretty sure. They're pretty sure. All right. I don't know if this is getting bigger or if this is getting small. it's not even getting controversial, really, because the Pope's down with it, if you pay any attention to him or care. A lot of folks have issue when we talk about stuff like this, and you're more than welcome to, okay, whether the Pope thinks it's fine or not. Because I know there's other religions, obviously, in the world. But most folks view the Big Bang as the beginning of what? That was a question. Time. Ooh, interesting answer. What else? Our galaxy, quite possibly. We're going to say time. We may as well also say what? Because they're linked. Huh? Space, yeah. Life after the galaxy. All right, so usually we say it's the beginning of the universe. All right. And yeah, it is, for all intents and purposes, the beginning of time and subsequently space. As long as you also believe or feel, we don't believe in science, that it's a singular event. Anybody keep up with Stephen Hawking when he was alive? Every so often I'll get a few hands there. He again was sort of pop culture and fairly confusing to listen to while still being entertaining. He introduced the idea that this was a recurring event, and subsequently blew a handful of minds there. So the Big Bang starts with the idea that you had an infinitely small point called a singularity. All right, and that singularity, that infinitely small point, contained all the matter, all the mass, all the everything that we have right now. Not just what you can see out the window and what you have at home, but all these stars and whatnot that we've been looking at for the last hour. Everything. And all the crap you can't see either. It was condensed down into that really teeny tiny point. And you're probably thinking, well, I can't imagine it didn't blow up. That's a lot of stuff. And I agree. They have good reason to believe that it happened about 13.7 billion years ago. You will see numbers higher than that. To my knowledge, they haven't proven or disproven the bigger numbers yet. But 13.7 is pretty common. It involves an expansion or an inflation. Okay? And most folks feel that it is, well, they know, they have data, that it is still expanding. Stars are moving. Any direction you look, things are moving away from us, which is really the only way we can measure stuff, right? As far as we look, things seem to be moving away from us and from each other. So they think that implies that it is still expanding. Now, how could we believe such an outrageous thing? That everything that now exists was into that teeny tiny little, even smaller than a pinpoint. Because you all believe in thermodynamics, right? Nobody argued with me when I said you can neither create nor destroy matter the other day, 2 months ago. Does anyone not believe in thermodynamics? Persecute you. Come on. Hands up. Yeah. No, it's absurd to even say that, right? But it's a very simple reason why, if this is true, you can neither create nor destroy matter, that everything that exists always has existed. Now, that doesn't necessarily support the Big Bang, mind you, but it does at least remind you that everything that's out there, everything you can see, always has been. Okay? So when we throw the Big Bang into the mix, that just tells us that that was all down into that very, very, very tiny pinpoint. A ways back, they made this map. And even though it doesn't look like it, this is a map of the universe and of the background radiation, the general sort of static that's out there. Again, you guys, I don't think ever grew up with a TV that you could turn dials on, but you've seen it on TV and possibly heard about it. And even radio stations, I don't think you could get static on anymore. But when you turned in between channels, there was static. On a TV, you got to see that static. It was a bunch of white, gray, and black dots. On a radio, you just heard it. Some of that was actual residual from the Big Bang. The universe is not at absolute zero. It's above absolute zero. And somewhere in there, with probably 3 other reasons, is again yet another reason they feel that the Big Bang happened. Because there's a temperature out there. It's still cooling off. The thing was so damn hot that 13.7 billion years later, there's still embers. And again, we could record those embers on our TVs and our radios. They found this out quite by accident, actually. There's a movie I used to show. I don't know how I used to show all these movies. I fraction of the time that I used to have. They only took a week away from us, but somehow I just can't show the movies I used to show. Anyhow, there was a Bell Laboratories, and they had a huge, it looked like a megaphone, all right, but it was really a satellite dish sort of telescopy thing. And it was over in Jersey somewhere. But they had to aim the damn thing over Manhattan. And they kept getting all kind of static, and they're like, well, Manhattan, duh. So they figured out a way to subtract that. They aimed it slightly higher. They did a handful of things to compensate for it, and they still kept getting this static no matter where they turned their scope. And again, someone who happened to be thinking about this kind of stuff happened to hear about their data, and they put 2 and 2 together and kind of supported this idea. And then years later, they sent up a satellite on a rocket ship that actually mapped this stuff. I forget the name of the guy. Is it in the... No, of course, there's no photo credits on here. This was a mapping mission, and I produced this image, and they feel this is, sort of moments after the Big Bang sort of thing. So, oops. There we go. So after the Big Bang, that quick, we'll say, in an instant, elementary particles and antimatter were formed. You don't know what antimatter is. We're not going to give you yet another vocabulary word, but you had heard of elementary particles. You know that these are the precursors to protons and neutrons. You know that they are electrons. So in an instant, we had the fundamental building blocks of matter. All right? Too hot for protons and neutrons, too hot for stuff to fuse together. Oh, I forgot my Big Bang joke I usually tell. You know how hot it was. It was, first of all, there was no, we're all so used to Star Wars, right, and explosions. There was no flash. There wasn't even a bang because it was too hot. You now know that those are all wavelengths, right? Sound and light, they're all wavelengths. It was way too hot for that. But they didn't want to call it the big, because, so anyhow, bad joke, science joke. By the end of the first second, they feel they was able to form protons and neutrons. And eventually they work their way up to the simplest elements, right? Hydrogen, helium, whatnot. Took about 400,000 years. These numbers seem really abstract. I get it. I don't want to say I share the same doubts as you do, but I share the same, really, that's, kind of specific. A lot of people have studied this stuff, okay? That doesn't mean it's 100% right. That doesn't mean by the time your kids are in school, they're going to hear a different number. But it's really what, the folks in charge of this feel that it is. So about 400,000 years later, let there be light, okay? Light is higher wavelength than noise, so we still haven't heard that explosion. But finally, photons have shown up. And as I said, we've got our elements as well. What number is that? Come on, everybody. What number is that? Good. 200 million. Good. Every so often I'll hear 200,000. Just want to make sure we're all on the same page. Why is it a trick question?
I don't want to say it because it's going to be not right.
Just knowing, seeing if you guys could count your zeros. About 200 million years later, they feel the first stars formed. First stars were super huge things. They were brighter than we've ever seen. They because they were so huge and bright, they burned out super quick, live fast, die young, that kind of thing. And they came in and out of existence way quick. Okay, I told you the sun. If you believe solar nebula theory, the sun formed about 4.5 billion years ago. I told you it's got about 4 to 5 billion years left. So you're looking at I'm sorry, did I say billion? Yeah, billion. Years ago. So, that's really slow by star standards. We've come a long way. These first stars were nothing like that. Super quick. Super quick. So, as material began to cool down, continued to cool down, the elements came together. That same thing I mentioned in the nebulas, how attracting one another gives them more mass, so more things are attracted to them. That same process happened as we were putting the universe together. All right? And that allowed stars, basically it allowed nebula to form, and then from those nebulous stars formed. What's still perplexing them is why there is a structure to the universe. That they can't really wrap their brains around. Why wasn't it random? Again, I don't know, that they'll ever sort that out. I personally don't know that we need to solve every riddle when it comes to this stuff. But there is a structure out there, and they're kind of confused as to why. And not that it looks like any of you are particularly digging this, but if some of you are in the backs of your brains, there's a field that you could certainly go check out, because we need some smart folks to think about that. And as I implied earlier, this is a process that's gone on and on and on. Nebulas come and go with supernovas. They feel that our sun is probably a third generation. And at that point, our galaxy came along as well. So was there a galaxy in the beginning? A little bit after, but our galaxy probably not. Our star, they feel much later. But there were stars, there were galaxies. Galaxy, by the way, a word we didn't really define, okay? Just for the record, it's a grouping, okay, of stars. That's what a galaxy is. I always forget to do that, and I should add a slide for it because I gave this talk one semester years ago, and at the end of it, right about now, somebody raised their hand. They're like, I'm sorry, I hate to ask this question at this point, but what is a galaxy? And I said, oh my gosh, I'm so sorry. And, you know, sometimes you forget what isn't necessarily in people's knowledge bases or backgrounds. So I assumed everybody grew up hearing the word galaxy a whole bunch. So, all right. So that's what a galaxy is. All right. We've got a handful. I know we're getting close to running out of time. We've got a handful more slides I'd like to just kind of pound through. If nothing more than this borders on the theoretical, and which means not necessarily so much to remember for the test. So we gave you, what, 13.7 for the age of the universe, or the Big Bang, or the 14.7. The running average goes between 12 and 15. All right. Told you there were some older, there's some younger. You see 12 to 15, and we're going to use that just for argument's sake right now. And we told you it started at a pinpoint and that there was a big explosion, right? And you guys are all super smart. You know about the speed of light. You know that stuff out in space travels at the speed of light. Why wouldn't it? It's light for the most part at this point anyhow, right? So one would assume that and you also know that the universe is expanding, right? So you know all these givens. So we have a pinpoint, we have an explosion, and we've let that clock run for 12 to 15 billion years. So one would think that if you move from point A to point B for 12 to 15 billion years at the speed of light, that you should be 12 to 15 billion light years away, right? It's that old story problem you hated in third grade. It's still around. The train leaves the station traveling 60 miles an hour. How far away is it after an hour? You weren't listening to the question, but the answer is 60 miles, right? All right. So if you leave the Big Bang traveling at the speed of light for 12 to 15 billion years, how far away are you going to be? 12 to 15 billion light years. It's the same setup. All right. However, because you've read the bottom slide like 10 minutes ago at this point, however, it's not. It's significantly larger. So that was yet another problem that they had to figure out. And guess what they did? They made up an answer. You'll see in a minute. I think it's made up. Again, they're the smart folks out there and in their field, and we need to trust them and everything I've been reassuring you about the whole time. But wait till you hear this answer. All right. So how do we know this? Let's pause for a minute. How do we know even that this happened 13.7 billion years ago, right? This 12 to 15. How do we know that? Well, that's how far we can see with the right equipment. That's how far we can see anything. At that point, in pretty much any direction we look, it ends, which is suspect enough, right? All right. But the reason that is, they feel, is because, well, that's as far as light has come. The thing about looking at telescopes and stuff far away is that you're actually looking at it a long time ago, because it takes time. Anybody, how long does it take for the sun's energy to reach the surface? Anybody know that one? It's random, but some people do. It's like 9 minutes. Okay? So for the sun's light to hit here, it takes 9 minutes. This stuff that is way farther away takes, in some cases, 13.7 billion years to hit us. We can cheat with telescopes by looking ahead and seeing that stuff out there where it more or less actually is. Anyhow, was there a question or just a... Yeah, exactly. Exactly. And again, think about our closest sun aside. All right, the closest one is 4 light years away. One of those in the I just forgot what it's called. Centauri system could burn out and we wouldn't know for 4 years. Yeah. That's what they say. That's what I'm getting out of it. I still think, because we also have a history of seeing supernovas, right? And we've got them recorded in history. I think China recorded the first one in way BC. I think supernovas are in real time. I'm not 100% sure. And I've talked to a handful of astronomers on that one, and I've gotten really not satisfying answers. But supernovas aside, yes, that's true about a star, fading out. If you and I are right in our understanding right now, you wouldn't see that flash from the supernova for 4 years, which is probably right. But so I still argue when they say, the first supernova was 4,000 years ago. Well, no, it was however far away that star was plus 4,000 years. That's always been my argument. But anywho. So anyhow, back to this. All right. So we could see that back that far. That's how long light has been traveling. So that's how old the universe is. You dig? We on the sort of the same page there. That's why they believe that. All right. So they couldn't figure out why it's actually significantly farther. How do they know it's bigger if they can't see that far? Math. The whole thing falls apart if it's only 13.7 billion years. It's interesting. Cosmologists are interesting folks, let's just say. But math is the reason why they're quite insistent that it's way bigger than we can actually see. So I told you they made up an answer. I wish you could do this in your math classes. All right. So they said, well, there must have been a point in time when things could travel faster than the speed of light. That's it. They said, well, there was a point in time that physics didn't apply. And I suppose, again, I'll give them the benefit of the doubt whenever I can, that sure, this is moment one, day one, time one. If we don't have particles yet, I suppose the rules of physics don't necessarily apply. But that just seems like a cop-out answer. I don't know. Oh, well, it must have just went faster than we think it can. That's called inflation. The volume expansion of 10 to the 76th in a fraction of a second. And a fraction of a second is way quicker than my snap. Since that initial moment of expansion, of inflation, expansion has slowed down to the speed of light. Again, they say. Because don't worry about those. I'm going to show you a pretty picture. So all of this, well, let's jump to here. Here's the 3-minute mark. So we go from this to this in 3 minutes, and in the last 14 billion years, we've only gone that much farther. So to give you some idea of what I've been babbling about, this expansion all happened way faster than the speed of light to way bigger than it should be in just moments in the whole picture of things. I have 5 more minutes or 2 minutes? God, I wish I could see my mouse. All right. So going back to Hubble, they named that telescope after a really famous astronomer, Edwin Hubble. He was one of the guys, along with a Catholic priest and Einstein, who walked into the bar, had a conversation, and decided this was a thing. Talk about a meeting of the minds over a beer, mind you. All these amazing things discovered over a beer. in a sandwich, probably. But anyhow, Hubble he was in like 20s, 30s, 1920s, 30s. Had access to an amazing telescope for the time. And I don't know that exactly it's what he was looking for at the moment, but what he did realize is that he was the guy that found out that no matter where you look, things are moving away from us. Remember I told you that a couple minutes ago? He's the guy that figured that out. And he figured that out because of something called redshift, all right, which we're going to show you in a moment. And he also found out that the farther something was away from us, the faster it seemed to be moving. So even more shift. The problem with that, and he was well aware of it, is that if you did the math and if you found a star or a galaxy far enough away from us, it would be receding faster than the speed of light, which again, we shouldn't be able to do because we still believe in physics, even though in the first moment we didn't. So what's redshift? It's that spectrum, light spectrum you know and love, okay? So we know what elements stars are made of, and we also know that if a certain element should glow a certain color. They know that, okay? It's called spectroscopy. It's a whole nother lecture. Trust me on this one. Certain elements glow a certain color. All right, neon signs, for example. Anywho, stuff was showing towards the right of what it should show. And the farther away it was, the farther to the right it was showing. And that's where he realized that, okay, I know this is hydrogen and it should be this color. Why the hell is it yellow instead of green, for example? I'm just making up colors at this point, but you get the idea looking at this. All right. So he put two and two together, came up with this idea. Doppler effect is also workable with sound. That's why you hear a siren coming at you and it changes pitch. You have all noticed that. That's the easiest way to figure out Doppler effect. And this Hubble's law is the version of that with light. All right. All right, so hopefully you've all been watching this little thing on the screen here. I'm going to let it run for another moment or two before I talk about it, and then I promise you we will end. So, imagine you're sitting there one day in your kitchen reading the New York Times, drinking a cup of coffee, whatever you read in the morning. Your phone nowadays, but this was 50 years ago. And you're watching a loaf of bread rise, getting ready to bake it. This is a loaf of raisin bread. Dough. And this is actually what they used to figure this problem out, Hubble's problem. So we're going to look at this raisin bread on time 1, which is right now, and at time 2, which is right now. And you got a centrally located raisin, and then a raisin to the left and a raisin to the right. Stand up, sit down, fight, fight, fight. All right? And on time 1, you got 5 centimeters to the left, and I think 10 centimeters to the right. It's going to come back around here in a moment ago. All right? And then, as it expands, I want you to notice that the raisin on the left is 10 centimeters away, and the raisin on the right is 20 centimeters away. So we're going to time it here. All right, 2 seconds, we'll say, between time 1 and time 2. The raisin on the left moves how many centimeters in 2 seconds? 5. The raisin on the right moves how many centimeters in 2 seconds? 10. Is that raisin on the right moving any faster than the raisin on the left? Is there any conceivable way possible that it could? I mean, given the fact that, yeah, okay, bread could rise unevenly, blah, blah, blah. None of that. But here, on this example, is the raisin on the right moving any faster than the raisin on the left? No, absolutely not. Okay? So what he's seeing was an apparent acceleration. He wasn't breaking the rules of physics, okay? It's really just a doubling that is all we're seeing. If you had $1 in your pocket and you had $5 in your pocket, and I said, I'll double everybody's money, some of you are going to get more money than others. Some of you are going to get less money than others. So it's a function of the original distance. So that apparent, remember we said the farther they were away, the faster they looked like they were going? That's why. He did not live to see this. I'm sure he watched many loaves of bread raised in his time, but it took someone else to put 2 and 2 together and get that answer. So, kind of simple, kind of neat. So you don't have to always be like, super scientific with your experiments and all that stuff. Sometimes it just comes to you. All right. I told you I'd wrap up, and we are. So, the galaxies aren't moving. The stars aren't moving. It's space that's expanding. That blackness in between the stars and the galaxies is what's expanding. And it's taking those galaxies and stars along for the ride. You've seen these 80s rock stars with their sequins and their spandex and all that stuff, right? And you're also around now to see them putting it on when they're 50 and 60 years old. And those sequins are a lot farther apart than they used to be, aren't they? Okay. It's the same idea. That spandex is space. And all those glittery things on their spandex are these stars and galaxies and whatnot. That also allows you, this knowledge also allows you to get around some of these perceived flaws in the rules of physics and whatnot. Does it answer everything? No. But it's getting closer to it. Getting closer to it. So when you hear the fabric of space and time, this is what they're talking about. Okay. So, a lot of history there. All right. A long lecture. I appreciate you guys sticking with me on this one. And if I could find my mouse, I would stop this dang thing.